Okay, lesson 2.6, rate of change problem. So now we're taking our ability to differentiate certain functions and applying it to real-world situations. So you get introduced to things like terms that they use in business or an economist would use. So if you're going to school for business or economics, these are terms that would come up. Physics, kinetics, those kinds of things. There's a problem that deals with electrical currents. But before we go, we're just going to take down a couple of notes on mostly terms and terminologies. So this is, I guess, derivatives of business functions, or we can just call it business functions. So it's lesson 2.6. It's called rate of change problems. 2.6, rate of change problems. And some business functions. We're going to do the function over here with a brief description and then its derivative over here. The derivative of a business function is called a marginal function, but we'll write that down when we get there. So the first set is functions that you're actually really familiar with already. You have a cost function, which is C with respect to X. So that's the total cost of producing X number of units of a product or service. So this is of producing X X units. That's of a product or of a service. And the derivative of that then is called the marginal cost function. It's represented as C prime of X or dC by dx. So it's the rate of change in cost with respect to the number of units being produced. What does that mean? This is the instantaneous rate of change of the total cost with respect to units produced. We'll say the number produced. So why is that helpful? Well, that would indicate, for instance, your optimal production numbers in a day or something like that, or your optimal production numbers on the year. At what rate of production are you the most efficient in, for instance, cost per unit to produce? Okay, good. The next function that you are familiar with is going to be the revenue function. Revenue, which is capital R with respect to X. Revenue function, X is the number of units sold at a price, R of X equals X times P of X. So this is X is the number of units sold and P is the price with respect to X. So in this case, the price is another function that could change based on the number of X's produced, things like that. So I could have done that one. I could have done the P of X first to kind of explain what that is. But anyways, revenue is the number that you sell times the price that you sell them for. That's the money that is going to be brought in. Money brought in based on number of units sold times price per unit. So the derivative of the revenue function is called the marginal revenue function. It is denoted r prime of x, or dr by dx. And again, that would give you the instantaneous rate of change of the total revenue with respect to, so the instantaneous rate of change of total revenue with respect to the number of units sold. What does that mean? Well, that means at any point, if you have your revenue function, you can find out when are you earning the most quickly. So when is your revenue increasing the most? So you could predict when you're kind of plateauing, or at what number of units is your profit slowing down, or when are you declining, those kinds of things. The rate of change of revenue with respect to the number of units sold. And the last one we're going to write down is the profit function. Profit function. So profit, P with respect to X, is your revenue, R of X, minus your cost. So it's how much money comes in minus how much money it cost you to produce or offer your service. So this is profit from the sale of X units. So X is a number, that number of units. X units of a product or a service. And it's a difference function, which you can see. Which means that our derivative is called the marginal profit function. Marginal profit function. It is denoted P prime of X, or dP by dx. And it refers to the instantaneous rate of change of total profit with respect to number of units sold. Okay, there's three basic terms. We're talking about cost, revenue, profit. We're familiar with those. So marginal cost function, marginal revenue function, and marginal profit function are the names of their derivative functions. Preceding all of this, I didn't write it, but preceding all of this, you'd also have P of X, which is the price function or the demand function, which basically is just the number of units that can be sold at a particular price, X. Maybe we should write that. I'll change my color to be a little more consistent. Demand function. Demand function is lowercase p of x, where p is the number of units sold at a particular price X. So this is like if your product is, if your cup of coffee is selling at $3 a cup, how many will you sell? If it's selling at $1.50, how many will you sell? And then this demand function fits into your revenue function, which then fits into your profit function. Okay, so they interact in that way. I guess you could take the derivative of your demand function as well, and you'd get, the rate at which your sales of individual cups of coffee are increasing and decreasing with respect to the price of the cup of coffee. I think we did a problem like that earlier, the cup of coffee thing. Okay, example number 1. Example 1. We're going to use the demand function. So we have a company that sells 1,500 DVDs per month at $10 each. I'm going to jot down some of the important information. 1,500 DVDs at $10 each. I'm pretty sure they're out of business at this point. Market research has shown that sales will decrease. Sales decrease by 125 DVDs per month for every 25-cent increase in price. So we have a price increase for every increase of $0.25. Okay. So we have our starting numbers. So we have a basic demand function. Right now, they're bringing in 1,500 times 10. Or I should say they're selling 1,500 DVDs at $10, and we're going to find out how many they sell at different prices, essentially. So we're going to see that demand function in action. The first thing we're going to do, A, is determine the demand function or price function. Those are the same thing. So the demand function is P of X, where P is the number of units of a particular product or service that is sold at a particular price. So first, we're going to have a couple let statements. We're going to let P be the price of 1 unit. Let P be the price of 1 DVD. We're going to let X be the number of DVDs sold per month. So this number, this 1,500 DVDs, is per month. Per month. And we're going to let N be the number of price increases, the number of 25-cent price increases. Okay, in order to express P in terms of X, we actually need to use two statements, 2 equations, 2 expressions here. What can we say? Well, X, if X is the number of DVDs sold per month, then we know that's going to be, so X equals, starting at 1,500, but it's going to go down 125 DVDs for every price increase. So 1,500 minus 125N. The second equation that we can come up with is P. P is the price of 1 DVD. The price is also changing. The price is going up 25 cents every N. So we start at $10 and we go up 0.25 N. And now we want to express P in terms of X. Express P in terms of X so that we get a statement for P of X. Well, in order to do that, we need to take our first equation and express n in terms of x. So we need to rearrange equation 1 so that we can then sub that in for n in equation 2. So in equation 1, we need to express n in terms of x, which basically means that we're going to isolate n by adding and subtracting, multiplying and dividing things. So first thing we're going to do is subtract 1500 from both sides. So we end up with x minus 1500 equals negative 125n. And then we can divide both sides by negative 125. Or what we can do first, and I'll just do it 2 in 1 steps. Because I don't want the first term to be negative, or because we don't want to have a negative in the denominator, I'm going to actually multiply both sides by negative 1. So that's going to make this positive 125. That's going to make this positive 1500 minus x. So what we end up with then is 1500 minus x over 125 equals n. So that is equation 1. Now we've expressed n in terms of x, which means we can now substitute that into equation 2 in order to get p in terms of x. So in equation 2, we've got p equals 10 plus 0.25 times our expression for n, which is 1500 minus x over 125. This is pretty ugly, so we're going to simplify it. We're going to expand some things here. 0.25, so this is multiplication is commutative. This is 0.25 times both of these things. We could distribute it into the numerator, or we can just divide 0.25 by 125 to lose this denominator. So we got 10 plus 0.25 divided by 125, which is 0.002 times our bracket 1500 minus x. Now we can distribute 0.002 times 1500 is 3. And then we have negative 0.002x, which means that we can combine our ones here. We've got p with respect to x is equal to 13 minus 0.002x. So what does this mean? This is the price of one DVD with respect to the number of DVDs sold per month. So this is the demand function. This gives the price for one DVD when X number of DVDs are being sold. And then from here we can get our, in B, we're asked to get the revenue function. So now that we have a demand function, it took a bit of work. I'm going to leave it up there and just do B right here. B is to generate a revenue function. The revenue function, according to our notes, is x times p of x. So r with respect to x is equal to x times p of x. So we have x times, in brackets, 13 minus 0.002x. Distribute our x, we have 13x minus 0.002x squared. So our revenue function is a quadratic. And the goal of B is actually to develop a marginal revenue function and then find out what the marginal revenue is when the sales are 1,000 DVDs per month. So step 2 on B is the marginal revenue function, or marginal revenue when sales are 1,000 DVDs per month. All right, the marginal revenue is just the derivative of the revenue function. So we take r prime of x. The derivative of this function is 13 minus 2 times 0.002, that's 0.004x. And we need to then sub in 1,000 for x. So we've got the marginal revenue function at x equals 1,000. Should copy down what we have and sub 1,000 in for x. Multiplying by 1,000 is moving the decimal place 3 places. So 1, 2, 3. That's going to be 13 minus 4, which is 9. What does that tell us? It tells us that when sales are at 1,000 DVDs per month, the revenue is increasing at a rate of $9 per additional DVD. So if they're selling them, if they're selling them at this price, so when they're selling 1,000 DVDs per month, at that point, every additional DVD is bringing in $9 more for the company. We can make a note of that. So what does this actually mean? Revenue is increasing at a rate of $9 per DVD sold. Okay, I cleared my board and just wrote down the functions that we've already figured out. C says the cost of producing X number of DVDs is given by C of X is equal to negative 0.004x squared plus 9.2x plus 5,000. And we need to determine the marginal cost when production is 1,000 DVDs. So marginal cost when producing. So remember, this is not the cost of producing. This is the marginal cost when producing 1,000 DVDs. It's the rate of change of the cost of producing a DVD. So you'd kind of assume that the more DVDs you produce, the cheaper it will get. But we also notice that it's a quadratic. So at some point, it's going to get more expensive again, depending on the number of DVDs that you produce. Okay, so marginal cost means we're taking the derivative of the cost function. The derivative of the cost function. So we've got this 2 being multiplied out in front. That's negative 0.008x plus 9.2. The derivative of 5,000 is 0 because it's constant. And then we're trying to find this out again at 1,000 DVDs. So the rate of change in the cost of producing DVDs when you're producing 1,000 of them is, just sub in 1,000 wherever we see x. Check it in the calculator. We get 1.20. So when producing 1,000 DVDs, the marginal cost the marginal cost is $1.20. So, and nice. So that is the cost of producing. That's the rate of change of the total cost. So this essentially is the cost of producing the thousandth DVD ish. So it's the rate of change of that. But we can find out exactly what the cost of the thousandth or the 1001st DVD is, and that's what we have to do in D. Actual cost of producing the 1001st DVD. So here we're going to use the total cost function, which is right here. We're going to find out the total cost of producing 1001 DVDs and subtract that from the total cost of producing 1000 DVDs, and that will give us the exact cost of producing the 1001st DVD. So there's our cost function. We're essentially going to be doing this. The cost of the cost of producing 1001 DVDs minus the cost of producing 1000 DVDs, which is just copying down this formula twice and subbing in 1001 the first time, and subbing in, and I'm going to jump to a new line because we're going to run out of, am I going to run out of space? I could probably squeeze it in. And then subtracting the cost of producing 1000 DVDs. And if we carefully work that out, you could put this whole section in your calculator and then subtract this whole section in your calculator, and we would get 1.196. So what does this tell us? It tells us the actual cost of producing the 1001st DVD is $1.19.6. So the point is to note the similarity. This was a lot easier to take the derivative of the cost function and sub in 1000, and you get the rate of change at that point, which translates into or converts into the cost of producing the next DVD, and then the next DVD, and the next DVD, and the next DVD. So you can find out what your cost is like. And then there's a note that just says that for large values of x, which I would say 1000 is a large value of x, the marginal cost, so what we found out here, the marginal cost when producing x items is approximately equal to the cost of producing one more item. So the marginal cost at 1000 is pretty much the same as the exact cost of the 1001st DVD. Last step for this one, E, we're going to deal with the profit function. Determine the profit and marginal profit for the monthly sales of 1000 DVDs. Profit and marginal profit. 1000 DVDs monthly. All right. Profit function. We know how to build the profit function. P, capital P, with respect to X, is your revenue, R of X, minus the cost, C of X. So the profit function is R of X, which is up here, 13x minus 0.002x squared, 13x minus 0.002x squared. We're going to subtract our cost function. I'm going to put it in brackets because this negative is going to apply to all the terms. Cost is right here, negative 0.004x squared plus 9.2x plus 5,000. And when we simplify that, again, this becomes positive, this becomes negative, this becomes negative. We end up with 0.002x squared plus 3.8x minus 5,000. We can kind of interpret this, again, it's a quadratic, and even before you produce anything, your cost is $5,000. So $5,000 flat fee, you're in the hole essentially, and then anything you sell, you start to earn some of that money back. Our goal is to find the profit that they earn when they produce 1,000 DVDs or when they sell 1,000 DVDs in a month. So the profit at 1,000, you would just sub in 1,000 to each of these x's. I'm just going to write down the answer. Ends up being $800. So the total profit this month that you sell 1,000 DVDs is $800. Hopefully your store sells other things as well. So that's not going to get you very far. And we want to find the marginal profit. So we want to find out the rate of change of their profit per DVD sold at the point where they're selling 1,000 DVDs. So we've got P with respect to X, P prime, the derivative of the profit function. We have a simplified profit function here, so we just need to take the derivative of it. That is 0.004x plus 3.8. And to find out the marginal profit when 1,000 DVDs are sold, we just sub in 1,000 and you end up with 7.80. We're going to write a statement about these two things. When 1,000 DVDs are sold, the total profit is $800, and the marginal profit is $7.80 per DVD. So basically they could look at this and say, okay, if we sell 1,000 DVDs a month, we're making $800. That's not enough. But they might also look at this and say, okay, when we sell 1,000, if we're selling 1,000 DVDs per month right now, and every DVD that we sell is going to make us profit another $7.80, that's pretty significant. So that can motivate them to get on selling more DVDs. It can also kind of help them gauge maybe how much they can afford to spend on marketing, things like that, or afford to spend on having an employee in the store if it's going to bring in higher sales. Okay, in example 2, it's going to be a similar situation, but we're not going to need to use the demand function. So here we have an ice cream shop. They currently sell an ice cream shop sells 150 cookies and cream, CNC, cakes. You could probably just use the word cakes. It doesn't really matter what flavor they are. Per month. at a price of $40 each. A customer survey indicates that for each $1 decrease, sales go up by 5 cakes. I have a feeling they're going to be increasing the price. If they're only going up 5 cakes for every $1 decrease, then they're only going to lose 5 cakes for every $1 increase. And since they're selling 150 cakes, I think they're going to gain more money by increasing the price. But that could be wrong. That is wrong, actually. I'm just looking at it. Maybe I just shouldn't talk until I read it. Anyway, here we go. Step 1. Determine the revenue function based on the number of price decreases. So A, revenue. We know revenue is the price of each unit times the number of units sold. So the price of each unit is 40 minus 1x, where x is the number of price drops, or we can use n to be consistent. N is the number of price drops, which would mean we're actually finding r with respect to n. R with respect to n is the price, which is 40 minus n, times the number sold, which is 150 plus 5n. Okay, B says take the marginal revenue function, find the marginal revenue, which is just taking the derivative of the revenue function. And we can do that using the product rule. So we're going to take the derivative of the first, which is -1, times the second. And we're going to add the first times the derivative of the second. We can expand and simplify this. We distribute -1 to both terms here. We've got -150 minus 5n. And here we distribute 5 to both terms. We've got plus 200 minus 5n, which reduces to -10n plus 50. It's the derivative function of revenue function, marginal revenue. And in C, we want to find when the marginal revenue function is equal to 0. When is marginal rev equal to 0? And then what is the total revenue at this time? And how can this help our store owners? So just to think about this, why on earth would we be finding when the marginal revenue is equal to 0? Well, if the revenue function is a quadratic, and it's a negative quadratic, then it looks like this. And the marginal revenue, which is the derivative of the revenue function, represents the slope of the revenue function. And we're finding when the slope is equal to 0. Well, that happens right here. Happens at the maximum point. So solving the derivative function is the same as finding the vertex of the revenue function, which we did a lot in grade 11 and grade 10. So we're going to solve the derivative function. Solve r with respect to n equals 0. So -10n plus 50 equals 0. To solve this, we're just going to subtract 50 from both sides, divide by 10, n equals 5. So basically that tells us the n coordinate of this point is 5. So that is the number of price decreases that will maximize their revenue. So now to determine what the revenue is, revenue at n equals 5, we just plug that number back into our revenue function. R with respect to n equals 5. So we're going back into our revenue function. Anywhere we see an n, we're going to put a 5. So 40 minus 5, 150 plus 5 times 5. 40 minus 5 is 35. So there you have the price of each cake that would maximize revenue. And this second number of part of the product is actually going to be the number of cakes sold. 150 plus 25 is 175. So there's a lot of information there. If they drop it 5 times to $35, they're going to sell 175 cakes, and they're going to maximize their revenue, which is going to be $6,125. So when the price, therefore, when price is $35, revenue is $6,125. They'd probably still want to connect this to their cost and profit charts. I don't know if revenue is the best indicator to go by. I think maybe profit would be a better indicator. But that's that one. Example 3, apply derivatives to kinetic energy. So kinetic energy denoted by capital K is energy due to motion. Energy due to motion. When an object is moving, its kinetic energy is determined by the formula K with respect to V, where V is velocity, is equal to 0.5 mv squared. So we have K, which is measured in joules. M is the mass of the object, measured in kilograms. V is the velocity of the object in meters per second. So here we have K, which is our kinetic energy, measured in joules. We have M, which is mass in kilograms. And we have V, which is velocity, which is measured in meters per second. Suppose we have a ball. The ball has a mass of 350 grams. It is thrown vertically. We're going to be converting here, by the way, because we're talking in our formula. We have mass is kilos, and here we have mass is grams. Anyway, suppose the ball with 350 grams is thrown vertically upward at an initial velocity, V naught, initial velocity, of 40 meters per second. Ball thrown up, right? Its velocity function, maybe I'll put this over here, still talking about this, V with respect to t is 40 minus 9.8 t, where t is the time in seconds. So what do we have? We have an initial velocity going up 40 meters per second, but it is slowing down at a rate of 9.8 meters per second squared. Sorry, 9.8 meters per second. So if after 1 second it's still traveling up at a rate of 30-ish meters per second, then after 2 seconds it's 20-ish meters per second, and it eventually slows down and comes back down. And then it'll speed up on its way down. What do we need to do? We need to, A, express kinetic energy of the ball as a function of time. Kinetic energy as a function of time. So we're just going to take, we have k with respect to v, and we have v with respect to t, and we need k with respect to t. So what we have here is a composite function. We have the kinetic energy with respect to the velocity with respect to time. Which means that we're going to simply take what we know, which is the mass, the v of t, and we're going to sub it into our formula for k of v. So we have 0.5 times m, which we need to convert into kilograms, 0.35 kilograms, times v squared, 40 minus 9.8 t squared. We're going to simplify just the first part of this, 0.5 times 0.35, that's 0.175, half of 0.35 is 0.175, times 40 minus 9.8 t bracket squared. Again, we don't need to simplify this whole thing because we have the power to differentiate as it is, which is what B asks us to do. B. Let's find K. So now what we have is K with respect to T. K with respect to T. Can go there. Should be a capital K. So now we want to differentiate K prime of T. And we're going to use the product law here because we have one thing times another thing. The first function, though, is a constant. So its derivative is 0. So the first part, to take the derivative of the first times the second function, that just whole thing becomes 0. And now we can take the first function, 0.175, and multiply it by the derivative of the second function, which is, we're going to apply the chain rule, take the derivative of the outer function, which is 2 times the inner function, times the derivative of the inner function, which is negative 9.8. If we simplify this, 2 times 0.175, again, we're not going to fully simplify it, and then times that by, we're just going to combine our constants, times that by negative 9.8, we end up with negative 3.43 times 40 minus 9.8t. And then B asks us to find the rate of change of the kinetic energy of the ball at 3 seconds. So rate of change of kinetic energy at t equals 3. All we have to do is take our derivative function of kinetic energy and sub in 3 for t. And if we do that, basically just putting a 3 here and calculate it out, we get negative 36.358, and that is meters per second. Nope, it's not measured in meters per second. It's joules. So kinetic energy is measured in joules, And because this is joules, it's the rate of change. It's joules with respect to time. This is going to be measured in joules per second. What does the negative value indicate? Remember, it's a rate of change.
It's losing joules?
So it's losing kinetic energy. Its kinetic energy is decreasing. The negative value indicates
So it's moving less than slowing down?
it's slowing down, essentially, which means it's still on its way up at 3 seconds. The negative value indicates that the kinetic energy is decreasing. It looks like it hits its vertex around 4 seconds. Its max height at around 4 seconds, which would be its lowest point of kinetic energy, because its motion is 0, slope is 0. Then it would speed up on its way down, in which case kinetic energy would be growing. Have you learned about potential energy? So it would have the highest potential energy when it's at the top. And then its potential energy would decrease, and its kinetic energy would grow until it hits the ground.
Before.
Example 4. Example 4 is dealing with electrical currents. We have an electrical current with a resistance measured in ohms, represented by 150 over I, where I is the current in amps. So we have resistance with respect to amps, and we need to determine the rate of change of the resistance. So we're looking for rate of change of R when I, right, equals 10 amps. So again, it's a rate of change. So the first thing we're going to do is take the derivative of this. In order to take the derivative of a rational function, we first express it as a product of two functions with a negative exponent. So now dr by di, which is notation for the derivative of the resistance function, is the derivative of, just the first times the derivative of the second, and the second times the derivative of the first. Well, the derivative of the first is 0, so that whole piece of the product rule gets taken out, and then we're looking at just the first times the derivative of the second, which is -1 times I to the power of -2. We simplify this, we end up with, in the numerator, -150. In the denominator, we have I to the power of 2. Now to find the rate of change when I is 10, the notation looks like this. It's the derivative function where I equals 10. And we just sub in 10 for I, which is -150 over 10 squared, which is -150 over 100, which is -1.5. So when the current is 10 amps, the rate of decrease, because it's negative, the rate of decrease of the resistance is 1.5 ohms, right? There's my effort at an ohms symbol, per amp. So if you increase the amps, you would expect to decrease the resistance. So as you push more through, the resistance is decreased. There's a little note before example 5. It talks about density. So derivatives and linear density. I'm just going to read it. It says derivatives can be used in the analysis of different types of densities. So population density, which would be the number of people in a specific area. Color density, which is used in the study of radiographs. It refers to the depth of color in a specific area. Linear density, which refers to the mass of an object per unit length. So linear density. Linear density, which is equal to mass over length. So that is if you had, it doesn't really matter what, if you had a ruler, let's say, and the ruler is this long, you could find out the density per centimeter on that ruler. And then if you added centimeters, you would know exactly what the density is, and you would know the rate of change of that density overall, or the mass, overall mass of the ruler, things like that. So if you had a function, f of x, that gives the mass of an object over a certain distance, a certain length of that object, if f of x gives the mass of an object with respect to length x, then the average mass of the first x meters is f of x1 minus f of x2 over x1 minus x2. So basically, if you had an object that was long, doesn't matter how long, and you take it cut into its meters, then the linear density is mass divided by length. So you could take any part of this stick, let's say, and basically what you would be finding out is just the difference in mass from having, in this case, having 0 to having 1, 2, 3, 4 meters over, and then divide it by the 4 meters. That would give you the average mass. But you could do this anywhere along the object. So even if the mass of the object wasn't constant, even if the mass changed, like this thing got fatter and skinnier or dense, more dense or less dense, you could go from here to here. And then you would simply be taking the mass of this piece, subtracting the mass of this whole piece over 2. Essentially, you'd be taking 4 minus 2 or 2 minus 4, making sure you're doing that in the right order. That would give you the average density of any section along that stick. What does that mean? That means that, so let's say if this was, so this is getting us an average linear density, then the derivative p of x equals f prime of x is the rate of change of density at a particular length. So if the density of this object was changing along its length, then its derivative function would tell us how that change is occurring, the rate of change of that density. So in example 5, we have the mass in kilograms, and I'm going to cross this all out. The mass in kilograms of the first x meters of a wire is represented by f of x equals radical, and under the radical 3x plus 1. And we are going to determine the average linear density of the part of the wire from x equals 5 to x equals 8. So we've got a wire here, and we're going to go from x equals 5 to x equals 8. And we're going to get the average linear density. And then we're going to determine the linear density at those points and determine and find out what we can about this wire. So A, average linear density from x equals 5 to x equals 8. So we're just going to take our average linear density formula. Average linear density, which we said was take the value of the function at x1, which would be x equals 5, subtract the value of the function at x2, which would be x equals 8, and then we have x1 minus x2 in the denominator. So in the numerator, we just are going to fill in what we're doing here. We've got f of 5 minus f of 8 over 5 minus 8. So I'm just copying down the function, and everywhere I see an x, I'm going to put 5. So we've got 3 times 5 plus 1. That's nice of them. And subtracting radical 3 times 8 plus 1. Also a nice square number. And the denominator is negative 3. The numerator, our roots here are 15 plus 1, which will give us the square root of 16, which is 4. Then we have 3 times 8, which is 24, plus 1, which is 25. The square root of 25 is 5. 4 minus 5 is negative 1. Negative 1 over negative 3 is positive 1/3, or 0.33. So the average linear density for this part of the wire is approximately 0.33 kilograms per meter. Kilograms per meter. That's the average linear density for this section of the wire. So in part A, with this function, this gives us the mass of the first x meters. So if we subbed 5 in there, which we did, that means we got the mass from here to here, the total mass. When we subbed 8 in, we got the mass from here to here. Okay? The average mass from 5 to 8 is just the mass of the whole thing to 8 minus the mass of the whole thing to 5. And then divided by 8 minus 5, divided by 3. But in order to find out what the mass is at a specific point, that's where we're introducing a derivative function. So for B, we're going to determine linear density at x equals 5 and at x equals 8, and then compare them and see what they tell us about the wire. So in order to do that, we start with our function f of x, which is right here, and we need to determine p of x, which is the derivative of f of x. So what do we need to do? We need to differentiate f of x. In order to do that, we're going to express it as a power with a fractional exponent and then derive it. So maybe I can do that first. We'll go, if you already wrote that, you can probably just scribble it out for a sec. But you've got 3x plus 1 to the power of 1/2, and then p of x equals f prime of x. So we take the derivative of that. It's a composite function, so we take the derivative of the outer with respect to the inner and multiply it by the derivative of the inner. And we can reduce this. We've got 3 in the numerator, and then we have 2 times, so I'll just draw my quotient line there, 3 in the numerator, and then in the denominator we have 2 times the square root of 3x plus 1. So that is our derivative function of f of x, and that will give us the linear density at a specific point. All I have to do then is sub in p of 5, put a 5 in everywhere we see an x. I'm just going to work across here. So that gives us 16, which is 4. 4 times 2 is 8. That gives us 3/8, or 0.375 kilograms per meter. That's the density at that point. And then for the density at the 8-meter mark, we do the same thing. Sub 8 in wherever we see an x. That's going to give us, in the denominator, square root of 25 is 5 times 2 is 10. That's going to give us 3/10, which equals 0.3 kilograms per meter at that point. And then just talking about it, so the two densities are different, which means that the material that the wire is made of is not all one material. It's not all made of like pure aluminum or pure silver or something like that, pure copper. It's non-homogeneous or homogeneous, and it's more dense at the 5-meter mark than it is at the 8-meter mark. But we'll just say, therefore, material is non-homogeneous genus. We know that because the density is changing. If it were all one material, the density wouldn't be changing. Practice problems that you could be responsible for from lesson 2.6 come from page 137, numbers 1 through 18. Again, don't do them all. Read them through, try them here and there, ask for help when needed.